You're welcome to Maths 203. We're now in the second part of fundamental laws of integers. Okay, we'll be considering some lemmas, and which includes Euclid's theorem. Okay, there will be a lemma definitely before the Euclid's theorem, the fundamental theorem of arithmetic, congruence, Fermat's theorem, and Euler's extension of Fermat's theorem. Okay, so we begin with the theorem, which is called the fundamental theorem of arithmetic. I will need you to be able to state this theorem. So if you're told to state without proof the fundamental theorem of arithmetic, all you simply state is that every integer a is either 1 or can be expressed as a product of primes. So a equal to p1 times p2 all the way to pr. But if a has a second such factorization, say you have a to be equal to q1 times q2 all the way times qs, then s will be equal to r. And when the qi's are suitably renumbered, we have that p1 is equal to qi. So pi equals to qi for each i. So once you state that, you have stated the fundamental theorem of arithmetic. Okay. Next is the Euclid's theorem. The Euclid's theorem states that the number of prime numbers is infinite. That's what it states. So if I ask you to state and prove the Euclid's theorem, this is what you're going to do, which is what you see on the screen right now. So Euclid's theorem states that the number of prime numbers is infinite, meaning that there are many. You can't count the number of prime numbers. That's what Euclid's theorem is saying. So this is the proof for it. So first we assume that they are finite because we're saying they're infinite. There are many, so we're proving by contradiction. So we simply assume that it is that we have a finite number of prime numbers. So let's say we have them p1 all the way to pn, where n is a positive integer. We count all of them, we have up to n of them. So we've counted them, we have them to finite. So if n is this number n, which is written as n equals to capital N equals to the product of all the primes, okay, then one can easily construct a new number, say m, and this number m will be such that we just add 1 to the product of the prime numbers. See, you add 1 to it here. So if you add 1 to the product of prime numbers, it's obvious that this n will be smaller than m because this is bigger by 1. For instance, if n were to be, say, 6, and this is 7, definitely n is smaller than m, okay? So n is smaller than m, that's what we're saying here. So by the fundamental theorem of arithmetic, what does it say? Let's go back. The fundamental theorem of arithmetic states that every integer a, if you have an integer a, is either 1 or can be expressed as a product of primes, okay? So you have the primes here. So by the fundamental law, fundamental theorem of arithmetic, it means that the m is divisible by any of the primes pi, because you can express as a product of primes. Is that not so? So now it means I can pick any of the p's and it will divide my m because it's an integer, remember? Now supposing it is p1, so you can choose to pick p2, p3, whichever one of them you want. I have chosen p1. So supposing it is p1, it means that p1 will divide m, meaning that I can write it as p1 dividing p times 1, p2 times all the way to pn plus 1, because that's what we said it is over here, remember? That's what m is. Let's see. We said m was this that you see here, right here. So since we know that m is this, you simply just place your m value for m here. Okay, so p1 divides this. Now if p1 divides this, clearly there will be a remainder, which means there must be a remainder, and it is 1. So it means that p, and if you put them together, the GCD, the greatest common divisor of p1 and m, that which is this product, which is p1, is just 1, because that's the remainder 1. Is that not so? If you remember what we've done with the Euclid's algorithm, okay, that is p1 and m are coprime. So m is a new prime number. Did you see that? But we said before now, what was the assumption? That there are finite finitely many primes, that is, there are a finite number of prime numbers. But we just constructed a new prime number, which is m. So this is a contradiction. So the statement of the theorem is true. So that's all to the theorem. So to prove the Euclid's theorem, first you need to be able to state it. That is the fact that the number of prime numbers is infinite. So we prove by contradiction by assuming that we have finitely many number of primes. So they are finite numbers. So we say, okay, let them be P1, P2, all the way to Pn, n of them. So if there are n of them, we see that we can construct a new prime number by simply adding, well, we first show that we can write n as a product of the primes all the way to n. And then we constructed a new one, which we just simply added 1 to the product of the prime, which we called m. And we saw that n now will be less than m, which is just product of the prime. And then using this fundamental theorem of arithmetic, which you should be able to state, which is what we had seen previously, we saw that any of the p's, pi, any of the p's would divide m. We chose, in my own proof, I chose p1. You could choose p10, whatever n value you want it to be. But for me, I chose p1, and p1 divided my m. And I saw clearly that if that happens, there would be a remainder, and the remainder will be 1. Now that I have a remainder 1, and I know that this means that the GCD, greatest common divisor of P1 and P multiples of n plus the P's plus 1, which is P1 and m, is going to be 1, meaning that P1 and m are co-prime. And if they are co-prime, it means that m is a new prime number, which is contradicting our assumption that there is a finite number of primes. So with that contradiction, it's obvious that this Euclid's theorem is true, that there are infinitely many prime numbers. So now we go into congruence. What is the idea behind congruence? Basically, we're interested in keeping remainders, just like you saw in the Euclid's algorithm. So for instance, if you take 5 and divide it by 3, how many times will 3 go into 5? It will go 1 time, and the remainder will be 2. We did that in class, if you recall. And so we can write it as 5 is congruent to 2 modulo 3, meaning that it has 2 remainder whenever, so you see the 2, the remainder is here, whenever you divide by 3. We read it as 5 is congruent to 2 modulo 3. So that's how we read that. Okay, so there's this way of writing. So basically with the same thing I've just said, we say A is congruent to B modulo C, read as A is congruent to B modulo C. We've seen all of this in class when we tried using that. Now, for the ring of integers modulo m, that's integers, when you're taking remainders, when you divide it by m, any value of m could be 2, 1, just think of all the numbers you want. So when you divide modulo m, definitely the remainder will be within the 0, 1, 2, all the way to m minus 1. How do we mean? Now, if you divide a number, any number by 5, what are the possible remainders? Remainder is that 0, 1, 2, 3, and 4. You won't get 5 as a remainder. Okay, so if you take integers modulo 2, you divide by 2, clearly the remainder is either 0 or 1. Any number you divide by 2, your remainder will either be 0 or 1. If you divide by 3, the remainder will either be 0, 1, or 2. Same also with 5, all the way, and so on. So you can check that on your own. Okay, if you divide any number by any of this, just choose any value for m and check if your remainder tallies with what is stated there. So the next theorem you need to be able to state is what we call the Fermat theorem. Now, Fermat's theorem says that if p is a prime number, then a raised to power p is congruent to a modulo p for all integers a. Meaning that if I take a raised to power p and divide it by p, my remainder will be a. And if a is a prime to p, then a raised to power p minus 1, when you divide it by p, will have the remainder 1. So once a and p are primes, then if you divide a raised to power p minus 1 by p, you always get the remainder 1. Okay, that's what we're learning. And that's what the Fermat's theorem is saying. So you should be able to state the Fermat's theorem, okay? Okay, let's move forward now. Okay, next is what we call the Euler's extension of Fermat's theorem. And this states that if M is not necessarily prime, but A and M are relatively prime, then A raised to the Euler of M is congruent to 1 modulo M. That's what the Euler's extension states. It's basically just this, that if M is not necessarily prime, but A and M are relatively prime, then if you take A raised to the Euler function on M, it's congruent to 1 modulo M, meaning if I divide this A raised to the Euler function of M by M, it will give me 1. So what is this Euler function of M? So this is the Euler phi function of numbers less than M and prime to M. So this is repeated twice. It's the Euler phi function of numbers less than M but yet prime to M. So to find the Euler phi function or Euler function of M for a prime number P, we use phi P is equal to P minus 1 if it is a prime number. So for instance, if P were to be equal to 5, for sure your phi of 5, the Euler phi function, will just simply be 5 minus 1, which is going to be 4. Why? Because my P is a prime number. Okay, so that's a formula for getting the Euler phi function of your value when it is a prime number. Supposing it's not a prime number, you want to get the Euler phi function when it's not a prime number. So if it's not a prime number, this is it here. If it's not a prime number, you use this formula here. Okay, so it's simply saying M times 1 minus 1 over the first prime times 1 over the second prime. You keep multiplying, so there's a multiplication sign missing here. Keep multiplying till you get to the last of the primes, okay? So there's a formula, okay? When it is prime, when it's not a prime, and when it's a prime, you use this, okay? So let's look at some form. Okay, so examples. I have already solved this first one. We did the first one just now. The case of phi when P is a prime. Okay, so can we try when let's try for 13. Can we see 13? So P is 13. I'm sure you can find that easily because 13 is a prime number, so you just simply do phi of 13 will be equals to 13 minus 1, and your value is 12. That's quite easy. Once it's a prime number, it's straightforward. It's when it's not a prime number that you have to use the formula. So let's see what happens. We have an example on the screen here, and the example is that we're to find phi of 6. Clearly, 6 is not a prime, okay? So, but the prime factorization of 6, so what do you get when you factorize 6? You get it as 2 times 3. So if you factorize 2 as a prime number, so into a prime factorization like we learned from the theorem. Where is that theorem? Let's look for it. Yes, the fundamental theorem of arithmetic. It says that any integer a is either 1 or can be expressed as a product of primes, okay? That's a fundamental theorem of arithmetic. So from this fundamental theorem, I see that I can express my given value 6, though not a prime, as a product of primes. So I can get my prime, the first prime, to be 2, my second prime to be 3. That's why there's P1 and then there's P2, okay? So now that I found my primes, I just use the formula here. It's not, we're working with one that's not a prime, is that also? Because it's not a prime, I use this formula. So I have P1 and P2, so I just simply stop at this. This is where I stop my calculations from. Okay, so let's see what happens there. So our m we know is 6, so that's why there's 6 here. Our p1 is 2, that's why there's 2 here. And our p3 is 3, that's why you see 3 here. So you simplify yourself and confirm that the value you get is 6. You can also check on your own. I'd like you to try if you had phi of say 12, you can do for 12. So you can try for 12 and see what you get. Okay, so we have another example on the board here. On the screen, not on the board. We're trying to find the remainder using Fermat's little theorem of 3 raised to the power 125 modulo 11. That is, using Fermat's little theorem, you're given a value. You're told if you should find the remainder when you divide this. Let me check it again. You're to find the remainder when you divide this value, 3 raised to the power 125 by 11. Even you understand that, even your scientific calculator, if you keep going 3 times 1 times 3 times 3, how long do you want to do that for? Till you get to 125. That's going to be a long one. So we have to go and borrow Fermat's little theorem. What does Fermat's little theorem say? Let's go back to the theorem. Fermat's little theorem says that, here it is, here it is right here. Fermat's little theorem says that if P is a prime number, then A raised to the power P is congruent to A modulo P for all integers. And if A and P are prime, then whenever you take this thing, A raised to the power P minus 1, and divide by P, you will get a remainder 1. And that's what we're told to use to solve our given example. Our example is that 3 raised to the power 125, when divided by 3, what is our remainder? And we're to use Fermat's little theorem. So we are looking for, so we seek x, that's what we're looking for, which is our remainder. See, this is what we're looking for when we divide it by 11. So how do we do that? Now, by Fermat's little theorem, if A and P are prime, I can get this whenever I divide by P. I can get 1 whenever I divide A raised by P minus 1 by P. Okay, so let's look at our case now. We'll check what's our A and P. We need to find A and P from our given question here. Comparing this A raised by P modulo P. Let's see. Modulo P. I want to compare the two of them together. Let me just clean it. Let's make it clearer for all of us to see. It's a little muddled here. Let's clean it so that we can find our C, so that you can see how I got my A and my P. Okay? So now, let's see P on my screen here. Okay, so usually you have A raised to the power P modulo P. So based on this, you can see that your A is going to be what? So this is A raised to the power P. This is the key one you use. You don't bother about the power because the power here is different, okay? So you have to be careful. You only use the ones that are the base, not the power ones, okay? From this, you can agree with me that A is 3 and my P is 11, do you? I'm sure you've seen that. You agree with me that that is the case, okay? Sorry, I'm coming. Okay, so we agreed that A is 3 and P is 11 based on what I've just shown you on the screen. So with that, you've seen how I got these values, okay? Okay, so now we want to find the remainder when 3 raised to the power 125 is divided by 11. So that's what I have here. So we need to verify first that 3 and 11 are prime. Are they co-prime? I'm sure you can see that they are prime to each other, okay? So in this case, they are co-prime. And neither 3 or nor 11 divides the other. So that's clearly the fact that they're co-prime. But what do we seek again using Fermat's theorem? We seek 3 raised to the power 125. What's the remainder when we divide it by 11? We have seen that A is 3 and our P is 11. And Fermat's little theorem tells us that A raised to the power P minus 1 is congruent to 1 whenever you divide it by P. So what do you think? We know what our A is 3 and our P is 11. So we want to get exactly this situation for our particular case, wherever A is, wherever P is. So we just substitute it. So our A is 3, our P is 11. So what is that going to be? It will be 3 raised by 11 minus 1, which is 3 raised by 10. So what's this going to be by Fermat's little theorem? It says that this is going to be 1 modulo 11. So we've only found for 3 raised to the power 10 that whenever I have 3 raised to the power 10, I'll get 1 when I divide it by 11. But we've not solved our problem. Our problem is for 3 raised to the power 125. We've only solved for 3 raised to the power 10. So how do we write 125? Because our power is 125, not 10. So how do we write it in terms of 10? What you simply do is use what we did when we were doing the Euler's function. If you remember in class, you simply just take 125 and divide it by 10. Okay, find out how many times it goes and its remainder, and see how you can express 125 in such a way that 10 will be in it. So this is it now. So 125 divided by 10 will go 12 times, and the remainder is 5. You can confirm that. So meaning that I can write 125 as 10 times 12 plus 5. Check if the two values should be the same. You'll see that they are. So meaning that by indices, 3 raised to the power 125 is the same thing as 3 raised to the power this value here. Because wherever I see 125, see it here. It is this value with 10 in it. Do you agree? So that's how I got what you see here. So using indices, because I know 3 raised to the power 10 here will give me 1, I made it my major concern. I just worked with it, I brought it out. This is what I've done here. And this will be 10 raised to, it will be 3 raised to the power 10, all raised to the power 12. You can see that on the screen. So now we know that this is simply expressing 125 in terms of 10, because I know by Fermat's little theorem, once I have 3 raised to the power 10 and I divide it by 11, I will get a remainder 1. So I try to write my given question, which has power 125 in terms of 10 in it, which is what we see here, by simply dividing my question, the one in my question, by 10. And then I got the remainder and expressed it in this form. After expressing this form, I now considered the question given, which is what you see here, and wrote it this way because I know 125 is what we have here. And then using indices, noting that 3 raised to the power 10 is going to give me remainder 1. So I worked with the 3 raised to the power 10. If you put a bracket, you get something like this, times 3 raised to the power 5. Using indices, same base. Okay, so that's how I got what you see on the screen now. Let's move forward now. Okay, so this allows us to break the problem. Our problem now, you are able to break it into smaller bits. Okay, so I can calculate 3 raised to the power 10 using Fermat's little theorem. You know it already. It is going to give me 1 whenever I divide by 11. So I need to check for 3 raised to the power 5 now. So also because I have seen 3 raised to the power 10, that's settled. Just wait, we'll sort that of 12 later. Everything raised to the power 12 later. Let's follow up on the 3 raised to the power 5. So now we need to find 3 raised to the power 5 modulo 11. What would we get? Okay, so you can calculate it step by step. When 3 is raised to the power 1, what do you get? You get 3 modulo 11, because if I take 3 and divide it by 11, it will go 0 times, and my remainder will still be 3. What of 3 raised to the power 2? It will be 3 times 3, which is 9. Divided by 11, what do you get? 9 divided by 3 will go 0 times, remainder 9. Okay, what if it's raised to the power 3? That's going to be 27, you agree? how did I get 5 modulo 11? If I take 27, because 3 raised to the power 3 is 27. Let's get it here. If I divide 27 by 11, it will go 2 times, and I'll have the remainder 5. So that's why I got the answer 5 modulo 11. What if when it is raised to the power 4? Remember, we're going all the way to 3 raised to the power 5. Okay? So 3 raised to the power 4, what do you get? 3 raised to the power 4 will be 81. Oh, 81 divided by 11 to go how many times? It will go 7 times, remainder 4. And finally, we have 3 raised to the power 5. 3 raised to the power 5 is simply 243. Okay, so let's check. How many 11s are there in 243? 22. What's the remainder? Remainder 1. Oh, so we have found it. So you might not necessarily need to do all of this part that I've done on the screen. I don't think you need all of this. I guess it's just to help you to understand. So because you only needed 3 raised to the power 5. So for 3 raised to the power 5, you just do 3 times 3 times 3 times 3, 5 times, and then check how many 11s there are in it and get the remainder, which is what we have here. So you found 3 raised to the power 5 is also 1 modulo 11. You found 3 raised to the power 10 is 1 modulo 11. We combine them together. So remember, what are we looking for? This is the question we're told to find. We're to find the remainder when this is divided by 11. So now we're combining it. We know 3 raised to the power 10 is 1 modulo 11. We know 3 raised to the power 5 is 1 modulo 11. So if you combine everything together, we know that this one here is 1. We know this one here is 1. 1 raised to the power 12 is 1. And 1 times 1 is 1. So the answer is 1 modulo 11. So the remainder when 3 raised to the power 125 is divided by 11 is 1. And that's your final answer. We have an example before us, a similar one, but a different question. And I'm sure if you rewind back the video and try to follow up what has been done thus far, you might have some questions, but during the class you could ask me. Or ask me online as you find easy for you. Okay, so we're to do the same thing using Fermat's little theorem, but now we have 5 raised to the power 135. We want to know the remainder when it is divided by 23. So again, using Fermat's little theorem. So what do you think are A? So this is A raised to the power P modulo P. Clearly P is 23 and our A is 5. And you can see that both of them are prime to each other, 5 and 23. There's no common divisor but 1. So they are prime. Okay, and we know Fermat's little theorem. It says that when A raised to the power P minus 1 is divided by P, it will give us a remainder 1. In our case, this is wrong. There's no P equal to 11. This is copy and paste situation here, so we're not using that. So in our case, we now have that A is 5 and P is 23, as you can see on the screen. Okay, so we do exactly that, what we did before. We just substitute for A and P. So A is 5, P is 23, so that's what you have here. So we got 5 raised to the power 22 is congruent to 1 modulo 23. Okay, so we found that whenever 5 is raised to the power 22, you get a remainder 1. But we want to find 5 raised to the power 135. So we need to write 135 in terms of 22. Simply, you take 135 and divide by 22. It will go 6 times and the remainder will be 3. Meaning that I can write it as 135 equals to 22 times 6 plus 3. And using your indices, just like we did in the previous example, you should be able to express it as you see here. Knowing that this goes to 1 and then you multiply this out and check how many remainders you get. Okay, so that's what we've done here. So it breaks it down nicely. We have calculated 5 raised to the power 22. We know it's 1 modulo 23. We need to find 5 raised to the power 3. Like I said before, you might not need to worry yourself about all the one by one. You just go straight here. 5 raised to the power 5 raised to the power 3 is 125. So how many 23s are there in 125? There are 5 of them. And what is the remainder? The remainder is 10. So you will get this here, that if 5 raised to the power 3 is divided by 23, the remainder is 10, meaning that 5 raised to the power 3 is congruent to 10 modulo 23. With that, we know what 5 raised to the power 3 is. We know what 5 raised to the power 22 is. We just substitute them, all the values back. So let's see how it is substituted. So our goal again is to find the remainder when this is divided by 23. We're able to express it in this form using our indices, as you saw in the previous screen. We're able to solve also that 5 raised to the power 22 is 1 modulo 23. We also solved that 5 raised to the power 3 is 10 modulo 23. So we combine everything together. So wherever you see 5 raised to the power 22, so we know what this is. It is this one here, say it here. 5 raised to the power 22 is 1. That's why there's 1 here, raised to the power 6. And 5 raised to the power 3 is 10, whenever you take it modulo 23. 1 raised to the power 6 is 1. 1 times 10 is simply 10. And so that's our final answer. Hence, the remainder when 5 raised to the power 135 is divided by 23 is 10. That's your final answer. Again, you can go through the videos, rewind it and take the step slowly if I was fast, and ask more questions online or during our classes. Thank you.